using soft lithography, right? So there is a lot of play around there to create finer and finer features. And as I told you, chemically you can do whatever you want, right? Instead of ending up with PD patterns, you can actually convert them to a very interesting chalcogenide system. This is PD4S. You can easily make PDS, which is semiconducting, but we found it interesting to make PD4S, which is almost metallic and extremely corrosion resistant. It can be, this is already dipped in corrosive atmosphere. There are nanowires inside the device, but still everything is conducting at least for a few minutes. And you can realize such patterns with soft lithography over large areas by doing this microchannel collapse technique, right? So what I'm saying is, starting with the conventional tools, there are possibilities to take the recipe to even finer length scales. So the basic philosophy is this: take a metal organic precursor and get into doing E-beam or micromolding in controlled atmosphere. You should be able to actually end up with any given material. Alloys, nitrides, oxides, sulfides, thin films of any pattern, and rest all will be volatile. It just goes away. So these are the kind of patterns we have realized in our lab, and having done with electron beam lithography and soft lithography, we have also tried out nano imprint lithography in collaboration with our collaborators in Singapore. I will just show you one or two results and then I'm closing. You can see, I already told you about nano imprint lithography. All that we have done is, instead of using a common thermoplastic flow polymer, here we have used a specialty ink, which is again a metal organic ink, and this is now related to benzyl mercaptan derived PD. So this is PD benzyl thiolate, and when this is coated on a substrate, it works wonderfully, and you can produce nano imprint lithography patterns there. Again, by gentle heating, you can take away the organic part and end up with the PD patterns, right? And so the process remains the same. This is the chemistry showing you that you can easily come to PD metal, starting with the metal organic precursor. And these are the process steps. I shall not go through these. I have already told you in the schematic before. And then you end up with PD patterns like this. And this is over an inch square area. You can see the color coming out because it's working like a diffraction grating. And here the feature size is of the order of 200 nanometer, done with nano imprint lithography. These are all direct. So you're not using an external polymer to pattern. You're using the metal organic precursor itself to pattern. And you can go on making much finer feature sizes. They're all down to around now less than 100 nanometer. And you not necessarily make grating structures. You can make pillars like this. You can see something has fallen off here. You can see these are all raised features, right? Raised features you can make and create some pillar structures of those. And darts, grooves, circles, rings, right? And even non-periodic. Look at this honeycomb kind of structure, even non-periodic. Depending on what kind of master you have, the technique is very versatile. What is more important is you can actually do three-dimensional patterning. Having done patterning, you can take it through next level of patterning using another type of mold on top and create secondary features here, and then do the baking, right? So you will end up with metal features which are carrying two different length scales. This is possible because first round when you do, it sets in. It undergoes cycles, thermal cycles, which are non-repetitive, which becomes an advantage when you're doing second level, third level patterning. And you see this is the first level patterning, and then up to this level we had brought the second stamp. You can see these finer features coming up, but this region is devoid of such finer features. So all these manipulative things you can try and create patterns. Just the last example. You can actually transfer patterns from one stamp to the other. You can do that, and you create stacks now. And as you do that, see these beautiful stacks here. So they are just colored differently just to aid identification. You can see here the first one, blue one, is below, and the red ones are running perpendicular on top. You can even create three stacks here. Green is the third stack. So you can create stacks like that using nano imprint lithography. These are all metallic wires, by the way. It's very difficult to realize such features with electron beam lithography or optical lithography, or even with common nano imprint lithography. Just because you are using direct imprinting here, it is becoming possible. And there are very interesting possibilities. If you create such metal features, you know, one level of patterning here, and on that you have created secondary pattern here, and already you are creating such nanostructures, which could be very interesting. I'll only spend a few seconds on this. You see here, if you look at rice leaf, people talk about lotus leaf. Rice leaf is also interesting. Grass, for example, is interesting. Grass, if you see, it has its features running parallel to the length of the leaf itself, and leaf actually tends to bend down to the floor, right? And so whenever a water droplet gets to nucleate or be there on the surface, it is made to roll down like this and just fall below. Probably roots are accessing the same water drop, right? So it is a sort of self-sustaining system, and it's all happening because it has anisotropic contact angles. You know, they are not spherical drops. In fact, it has slightly distorted droplets there. And similar systems you can create here using the secondary features. Contact angle from one direction is 130, from the other direction is only 90. You can create such interesting anisotropy in wetting. Where it is important? You want to have a metal pattern and have it hydrophobic. How do you make a metal pattern hydrophobic? Usually metals tend to be hydrophilic because they form always a thin oxide layer, right? So I haven't come across a metal surface which is hydrophobic. Purely because of this patterning possibility, we can realize hydrophobicity of the metals. So I think I have come to close now, and I must tell you what was not covered. I have not talked about helium ion beam lithography at all, and the self-assembly based methods I didn't talk. And there are specialty beam deposition methods. STM I didn't touch upon at all. Device integration also I didn't talk about. Okay, I mean, as you can see, this is a very vast field. There are a number of things here to deal with. This was only giving you a glimpse of what is already there and what is being pursued in the literature and what has been pursued in the recent past. Okay, so let us stop here, and I take questions. Questions? Please.
All the pen using the tape will be made of anything? How they will be manufactured?
Okay. AFM tip, the material is typically silicon nitride, common AFM tip, and that is done by a technique called FIB. I'm not too sure whether it is done by optical lithography. I don't think so. This is focused ion beam technique, which I didn't talk about. That is what is used to produce AFM tips. Is it so commercially as well, Professor Fisher? Gupta? Yeah? FIB? Yeah, yeah. Okay. But silicon nitride is one type, but there are variety of tip materials available. Any more? Where you commonly come across patterns, day to day, fine patterns? What are the finest features you are using day to day?
Chips and cell phones have chips. Gates are there, which are.
I mean, I'm saying something. You are right, but you know, I don't think they have, except the memory, the flash memory and all could be carrying very fine feature sizes. But something which you see with naked eye.
That drops during fall.
No, CD, DVD, right? CD and DVD have tracks which are typically a micron apart with a depth of around 150 nanometer spiral groove. Okay, any more? Should we close now? Thank you.